start the session with a small video on torsional irregularity by the time people join. There has been good response. Overall, 50 registrations are there, but how many will be taking it live? Uh, that we will see in next 10 minutes by the time that video ends. Okay, and after that we will start with the session. So the speaker for the session today, as you know, is Mr. Tajul from IIT Roorkee. He is a research scholar there, and he has also taken the course on performance-based seismic design, and he is a moderator for the sound seismic engineering group as well. So I welcome him, and I'll ask him to wait for 5-10 minutes more till I finish the demonstration of a small video, and after that we can begin the session. Yeah, Tajul.
Yes, sir. So should I start?
I'll just have a video, demonstration video. Uh, just a fundamental 10 minutes video is there by the time other participants also join. Right now we are 20 numbers. It has to 52. So we'll wait for 5-10 minutes more before starting the session.
Yeah, sure. You can go ahead with the video.
Thanks. So when my video is, my screen is visible, kindly let me know.
Yes, it's visible.
So is the full screen visible to all? Hello, is full screen visible to all?
I can see your screen. Others can respond if they are not able to see.
Yeah, it's
Yes,
visible.
sir, visible. We can see the screen.
Yeah, thanks. Okay, so we'll start with this small 8 minutes video, which is on a molar model. So let me know if audio is not visible. I will speak on the audio. Okay.
Sir, audio is not there actually.
Hello.
Sir, audio is not there actually.
Okay, so what has been demonstrated here is that where this gummy bear, red is a gummy bear that they have put as a load. Other side there is a weight. Okay. So there are two frames. On the gummy bear side, there is a moment frame which is less rigid. On the right side, there is a braced frame which is rigid. Okay, so they are now going to shift the eccentricity of the load, and will demonstrate that how you can have some uh, modification in your structural system, that is size of the shear wall, orientation of the column, bracing if it is a steel structure. So they are trying to regulate the stiffness between the two frames so that the torsional irregularity does not is reduced basically. One side is flexible, one side is rigid, and load is on the flexible side. So that is a stiffness issue demonstrated here. So it is translation in other directions because three directions are braced. On one direction it is flexible. That's why there is a torsion or rotation in that direction. This is the CM, center of mass. So this is the center of rigidity. So what he's trying to demonstrate is that the entire ductility requirement for the building has shifted on the rigid frame as the flexible frame is not able to resist it. So the building ductility reduces. So it is not able to reach to the ductility level that we are considering in our design. That is why torsional irregularity is not a good thing for the building. That is what this motion also shows that right side frame is more rigid. That's why it is giving higher resistance. Left side frame is very flexible, deforming, and it is not able to give the adequate resistance to the story force that is generated due to the earthquake. And torsional unbalance moment have to be taken by the rigid side, not on the flexible side. So that way the additional force has to be taken on the rigid side and entire building ductility value will reduce due to that, which we are not able to estimate physically. So the idea one is as we are not able to estimate the ductility of the system, uh, the code has given the torsional provisions to us, and if we want to maintain the ductility or solve the torsional irregularity problem, the solution one is that you increase the stiffness of the frame on the left hand side, okay, which is not braced, you can make it braced. That way the stiffness distribution will be equal on both sides. Or second option is you can reduce the stiffness of the braced frame, okay, so that it can both frames can participate in resisting the lateral load. So you can reduce the width of the braced bay, okay, that is the bracing can be in a smaller, sleeker bay, okay, if it is a steel frame. If it is a shear wall, you can reduce the length of the shear wall. If it is a column, you can regulate the stiffness till the motion becomes translational. Okay, so that is what two methods have been demonstrated through this MOLA model. So this was a small demo on that, uh, how the buildings can be uh, controlled with the behavior. The check to be done is the displacement should be within the limit. It should not, a member should not fail in shear by reducing the sizes, and orientation has to be corrected. So all these play can be done in this demonstration through simple model I tried to explain. So now Mr. Tajul will take over the session, and he will take it further into the aspect of the torsional irregularity. Yes, Tajul, we can start with the session now.
Yeah, thank you, sir. It was a nice video, in fact, to understand the torsion with some visual interpretation. And the many things what has been shown in this video, we have to understand how to interpret when we try to model our structure. So this is what we are going to learn today. And I request all the participants before starting the presentation, because there will be a lot of technicalities actually, and many of the terms what you are going to see in the presentation will be maybe you are seeing first time. So I just request you to be a little bit careful while listening, and we can discuss all the doubts after the presentation, whatever you have regarding what we are going to discuss. Okay. So let me share my screen. And one more thing, actually, we are going to discuss two topics today. One is the torsion, how to deal with the torsion, and another one is the mode shapes. You all know what is mode shapes when you operate softwares like ETAP, SAP, something, some like other softwares also for designing of your structure. But what we'll do today is to understand what actually this mode shape is and what they represent in physical terms, and how can you determine the mode shapes with some manual calculations apart from using software. So first we'll discuss mode shapes, then we'll go to the torsion. Okay, so I'll just share my screen now. I think the screen is visible to everyone.
Yes, it's visible.
Yes,
Okay.
yes.
So again, thank you everyone for participating in the session, and thank you, Bhushan sir, for inviting me to have this presentation here. So the first thing, as I told, we are going to discuss the mode of vibrations and fundamental periods, and how can we determine with manual calculations. So before going to the calculations, let us first, 1 minute. Let us first see what these mode shapes are. So as you can see here, these are the characteristics of deflected shape. It means when you apply some load to your structure, structure is going to deform. And the deformation, what you can see actually is not a single deformation actually, that is a combination of multiple deformation patterns. So it is like there are multiple quantities which are added together to give a final result. So that final result only you see when you see the deflected shape. So now the individual quantity or individual deformation shape that we call as the deflected shape or mode shape. So when the structure vibrates freely, means there is no resistance in the vibration in each deflected shape. So again, this should be in the harmonic motion. When we are talking about the mode shapes, we are talking about the harmonic motion. Means we are assuming that structure is vibrating with a harmonic motion, and each of the deflected shape is associated with a particular frequency. Those frequency actually we call as the time period, or means there is a relation between frequency and time period. So each frequency you can convert into a time period. So that is why each of the mode shape will have a frequency, so it will have a particular time period. The number of characteristics deflected shape is equal to the number of degree of freedom. It means, suppose you have a four noded structure. So if you consider 6 degrees of freedom in each node, so in four nodes, you'll have total 24 degrees of freedom. So your four noded structure can vibrate in 24 different patterns. So similarly, if you think about a structure like a 10-story structure with multiple bays, so you can count the number of degrees of freedom, and you can imagine that many different ways your structure can vibrate. So this is what it means. But when we analyze the structure, you usually specify the number of modes in your modal analysis definition. So mostly we give number of stories multiplied by 3. That many are sufficient. But it doesn't mean that you have only that many mode shapes available in your building. So that will be counted as total degrees of freedom multiplied by total number of nodes multiplied by number of degrees of freedom at each node. So that many mode shapes you will have in the structure. So let us little bit understand what is the meaning of harmonic motion, so that you better understand the mode shapes. So these harmonic motions are nothing but the oscillation of structure in a particular pattern from starting to ending without having any restrictions. Okay, it means, let's say this is your structure, and you have applied some initial deformation, let's say pi to 1, this pi to 1. So what I did, I have hold my structure here, then pulled it this direction, then after reaching certain quantity or amplitude, let's say at point A, then I have released my structure, and after that I didn't disturb my structure. So now the structure is vibrating freely. Okay, so this is what the harmonic motion means. it will not have any external effect. After having the initial oscillation, then it will start vibrating with with its natural properties. So now what happens? Suppose I have released at this point, so it will go in the opposite direction, then it will reach to some peak point, then again come back, then again going back, again coming back, like that. So until it stops, the stop when it will stop, depending on either you are stopping it externally or it has some internal energy dissipation in terms of like damping, you can say. So based on those conditions, it will stop. If suppose there is no energy dissipation condition available in the structure, it will keep on oscillating with whatever amplitude you have applied initially. So this is what happens. Now this oscillation means coming in this direction, then going back, again coming. You can plot in terms of XY plot, like that. So when you are plotting, your plot will be visible like that. So in X direction you have time, then in Y direction you have amplitude. So this is the amplitude we have applied actually. Now see, because of this application, how each of the stories are deforming, or each of the stories are oscillating. So here phi 1 is representing the oscillation of first story, and phi 2 is representing the oscillation of second story. So here you see the oscillation plot of second story, and here oscillation plot of first story. So what happens? One more condition is, in harmonic motion, each of the stories will reach their respective peak at the same time. What I mean to say is, if you compare the plot of first story and second story, so at 0 point, this was the peak at the first story, means at 0 time period, you can say this was the peak of first story, and at the same time this was the peak of second story, means this point. So this is represented by point A, as you can see here. Then if I go to some other time steps, let's say at point B, so at this point you can see here the first story is here and the second story is here. Although the amplitude of first and second are not same, but they are reaching their particular peak point at the same time. So this is what the harmonic motion means. And now the time period, how we can get the time period from harmonic motion is, time period, if you represent in terms of frequency, it is the time required to complete a cycle. So when I release from this point, it will go back and again come back to the same point. So the time taken for this oscillation, going back and coming back to the same point, that is called as time period. So this you can represent like that. If I take this cycle, here we can have multiple cycles depending on how many oscillations the structure is giving. Let's say I started from this point, then it is going in opposite direction, then again coming back to the same point here. So this is my one cycle. After that, again it is going from this direction, going to the other direction, then coming back and coming to the same point. So this is another cycle. So again you can represent from this point also. So if I start from this point, so it is going like this, then again coming back to the same point. So like this also you can count. So your time period and frequency will be related using this T is equal to 2 pi by omega. I think we all know this formulation. So you can calculate your time period if you know the frequency. So in structure, if you see this, we call as the first fundamental mode actually, when your structure is having the oscillation for all the stories in the same direction of your axis. So if this is your vertical axis, uh, first story and second story both are in the same side of your axis. So this we generally interpret as a first fundamental mode, means a translational mode. Similarly, if you go to the second mode, let's say this is second mode. Again, you are pulling your structure up to point A, then you are releasing. And when you release, it will start oscillating and going back to this point, again coming back like that. But in this case, you see, when your let's say your second story is at point A, at the same time your first story is at this point in the opposite side. Okay. Then when your second story is at point B, you see your first story is here. So both are reaching peak. That condition is satisfying. What we have discussed earlier in case of harmonic motion, all the points will reach their respective peak at the same time. So that condition is satisfying here. But the thing is, the peak is not in the same side. They are in opposite side and they are crossing just one time. Here you see this is the conjunction point where the direction is changing, and it is happening here for one time. So this again we say the second mode of our translational mode in structure, where your deformation pattern changes for one time with respect to the vertical axis. Okay, so these things again same way what we have discussed in the previous case you can interpret here. All the points are reaching their respective peak at the same time. So each of these harmonic motion and the corresponding deformation shapes we call is the natural mode of vibration. Why we call natural mode? Because this is the structural internal property. There is no external effect. As I said in the beginning, we are not applying any external effect once the structure starts oscillating. So the behavior or vibration will be completely governed by the structural properties, not with any external effect, like you are applying some external load or some wind is flowing. There will be no external impact like that. So that's why we call it as natural mode of vibration. Now, just as an example, I have taken the deflected shape of one of the structure what we are going to discuss little bit later. So the first translational mode, as I told, your structure will be deflected in one side of the vertical axis. Let's say if I consider this as the vertical axis, so my structure is deflecting in the left side of my vertical axis, and there is no point which is on the right side. Okay, so all the points are on the left side of your axis. So this is the first translational mode. Similarly, if you go to this one, again, let's say I consider this as my vertical axis. So if you start looking from the bottom, here you see these points. These points are on the left side of your axis. And from this point here, it starts changing the direction. And the points after that are going on the other side, that is on the right side of your axis. So the conjunction point is again just one time. So this is the second translational mode. Then you have this one. Here you see, if I consider this as my vertical axis, so you just observe the points here. This is changing at this point, then again going to the other direction and again changing at this point. So the intersection is happening for two times. So this is the third deflected shape. Then come back to this one. This, let us consider this is the vertical axis. So if I look at this point here, it is changing the direction. Then here again it is changing direction, and here again it is changing direction. So the intersection is happening three times. So this is our fourth mode shape, and so on. I have just considered only these four for demonstration here. Similarly, there will be lot of other mode shapes depending on total number of mode shapes available in your structure. Okay, so now same thing, the mode shapes, if we plot in terms of XY plot, it will be looking something similar to what you can see here. This blue line, let's say this is the first mode shape, where if you consider the vertical axis to be the story numbers and the horizontal axis the modal deformation parameters. So in the first mode, which is shown by the blue line, you can see all the points are on the left side of, it can be either left side or right side, it doesn't matter. In mode shapes, the direction doesn't matter, only the shapes and the pattern matters. So you can plot the same thing on the other side also, there is no problem. So don't go by the direction, just remember in mode shapes and pattern matters. Okay, so here all the points are on the same side, that is left side of your axis. Then the second mode, second translational mode, but here you see this is not second, this is mode 4, because these values I have taken from ETABS or some software where you are running your analysis. So this second translational mode will be your fourth mode in the software, depending on what is the mode shape condition in your structure. So here for my structure, I have first mode translational, second mode translational in other direction, then third mode torsional, then fourth mode again translational. So that's why it is fourth mode. But if you do not have this pattern, so depending on your pattern, this number may change. That you have to identify. So now this fourth mode is the second translational mode for this direction, whatever I have considered here. And this you can see in the orange line. So its intersection point with the vertical axis is happening for one time. And third translational mode, which is the 7 mode in your software, means in my model, may not be in your model. So this you can see with the gray line here. Intersection is for 2 times. Then you go to fourth mode, that is fourth translational mode, and you can see, you can count the number of intersection points 3 times. So this is how you have to understand the mode shapes. And similarly, this is shown for one direction. You have 2 orthogonal directions in your building. So if you plot the mode shapes for other direction, you will get something similar, maybe with different values. So this is what it means. And these mode shapes, again, again, this I have copied from the output of my analysis results. So you will not get in the software whatever I have shown here. It will be given in terms of displacement in mode shape. Okay. So this I have splitted for first mode, second mode, third mode, fourth mode, like that. You will not get same thing in software. That you have to understand, and you can extract if you want. Okay. So now we are going to understand how this mode shapes, whatever I have shown here, how mathematically you can present this. If you want to calculate, let's say you want to validate your computer model. Just few days back, I got a doubt from one of the participants in our last course. She was asking whether my computer model is right or wrong. Okay. So one way is to validate your mode shapes, whether it is correct or not. Sometimes if you are modeling wrongly, if your computer model is wrong, software doesn't know what is wrong, what are right. That we have to understand. Okay. So the result, what you are getting, if you have some doubts in that, this is one way to verify. If you can calculate the mode shapes and time periods mathematically, then you can compare your model and you can understand whether it is correct or wrong. Okay. So this is what we are going to learn now, how to calculate time period and mode shapes theoretically. So if you have attended our last course, you might be knowing this formulation. Total displacement of your structure can be interpreted as a multiplication of your mode shape matrix and your deformation vector. So this is not a single quantity. This is also not a single quantity, and this is also not a single quantity. This is matrix. This and these are vectors. If we extract this, it will look something similar to this. Now, in this extraction, what I have considered is I have a 40-story building, and only lateral modes I have considered, means lateral deformation I have considered, and other deformations I have logged. Means in one node there is only one deformation which is in lateral direction. So this way, for 40-story building, I will have total 40 modes, so 40-story deformations. So this vector is having a size of 40 by 1. Okay. Then for these 40 modes, now since I have logged other modes, so my mode shape vector will have a size of 40 by 40. It will have 40 columns and 40 rows, like that. Then you have modal deformation. This small q is actually representing modal deformation. It means what is the deformation in first mode, what is the deformation in second mode, what is the deformation in third mode, like that. Then if you multiply this modal deformation with this mode shape matrix, then you'll get total deformation. Okay. So all of you already know what is the multiplication procedure, or how to interpret the result of matrix analysis. If you have this mathematical formulation, I want to get U1. So what you'll do, you'll multiply this first row of this matrix with this vector. So you'll have phi 11 into Q1 plus phi 12 into Q2, like that, up to phi 140 into Q40. So this is what you get, what I have shown here. Similarly, you get the deformation of second story, then third story, fourth story, like that. So here you see the actual deformation. This is the deformation what you are going to see in your software. Let's say you have applied a lateral load of 100 kilonewton to your structure. Then when you open your output, the result what you see, that will be this one. Okay. This one you cannot see. This you have to understand mathematically. So how the software is getting this is adding the mode shape deformations of all the modes in terms of matrix multiplication with the mode shapes. Okay. So this addition actually not a straightforward addition. It is a SRSS rule or CQC rule. If you do not understand this one, we can have a separate session for this one to understand these rules, along with how to calculate the response in modal analysis manually. Okay, that also we can take up if people are interested.
Yeah, hello,
The,
Raju.
yes, please.
One question, you can answer it later. That
Huh,
we are having the stiffness K and mass M, from which we get the
huh,
eigen solution. Okay.
yes. Huh,
So that 12 EI by H cube, the formulation that we use. Okay.
huh,
So
huh.
software is also using the same way, or is some other way it is calculating the stiffness?
That
You
is
can
actually
just,
part of discussion. That is part of
yeah,
discussion already. So you'll understand.
yeah, thanks.
So just for the example, phi 11 in this expression multiplied by Q1 is the contribution by the first mode to the structural response. As I said, this is your structural response, and this is the contribution to this response by the first mode. Similarly, this is the contribution to this response by the second mode, and like that. Then like this you get the story deformations or other deformations. If you are considering all the degrees of freedom, similarly you will have other deformations also. So once you get the nodal deformations, then you can analyze your structure by knowing the boundary conditions, which are nothing but the nodal deformations. Okay, then you can calculate your member forces and moments, and for that you have to apply this expression where F is equal to K into U. So this U is nothing but this vector what you are calculating from this analysis. So you know this U and you know the structural stiffness matrix, then you can easily calculate the member forces. So it is just straightforward, but calculation will take time if you are doing manually. Software can do it faster. So now, if we understand the mode shapes and time periods, let us also understand what are the importance. The response of complex multi-degree of freedom system is simplified by modal superposition. What it means is this deformation vector is a complex phenomenon. What we do, we simplify this in terms of modal deformation, because modal deformation is giving the deformation of a 1 degree of freedom. Sorry, means single degree of freedom system, and it is easy to analyze a single degree of freedom system compared to a multi-degree of freedom system. So you have a single degree of freedom system, you find out the deformation quantity q1, then this q1 multiply with this mode shape vector, sorry, this mode shape matrix will give you the deformation for the actual structure. So this is what it means. If you want to analyze a multiple degree of freedom system which is complex, so instead of analyzing it as a single structure, you split this structure into a multiple single degree of freedom system and analyze those multiple single degree of freedom system which are very simple. Then you superimpose the response quantities in terms of modal superposition. So this is what it means, and to do that you have to understand mode shapes and you have to understand time periods. So what we do, we solve the equation of motion for the single degree of freedom system for each modes to get the modal response. Then we do modal superposition to get the structural response. Okay. So now you understand the basis of our structural analysis using any software. You take any kind of software for any kind of structure. All the software uses the same concept. You do the modal analysis to simplify the structure, then apply the superposition method to get the final structural response. And this happens only when you do the response spectrum analysis. I'm not talking about the equivalent static method, because that is just a one, that itself is a single degree of freedom system concept. So this concept, multiple modal superposition method, is only when you are applying response spectrum method. So this is what the mathematical interpretation of whatever we have discussed so far. You have general equation of motion, which is this one. So you have mass matrix. Actually, the all the quantities here you can see are either matrix or vector. So in the left side, all the quantities are matrix. In the right side, you have this as matrix and other two as vector. This is, although it can be a single quantity also if you have ground motion applied in just one direction, but it may be a vector if you have simultaneous ground motion in 2 or 3 directions, and this is a vector. Again, to understand this one, you can contact with me or you can refer our previous course materials. There, these things are explained clearly. So what it gives is, you have mass into acceleration, means we are just satisfying the equilibrium condition. Forces in one side should be equal to the forces on the other side, or you can say applied force should be equal to the resisting force. So here, this is the applied force, this is the ground motion intensity. So the applied force, if I consider, is the earthquake force is the inertia force. Ground acceleration multiplied by the mass of your structure will give you the earthquake force. So this is the applied force. It can be any quantity. Here we are representing in terms of earthquake force. Then on the other side, you have resisting force. You have mass matrix into acceleration, then damping matrix into velocity, then stiffness matrix into deformation. So these are the internal parameters, the structural properties. So in case of mood shapes and time periods, as I said, that we have to consider free vibration and harmonic motion. Means there will be no resistance to your oscillation. So what we have to do, we have to ignore this dissipation, because this damping matrix is actually dissipating your energy. So we have to ignore your damping, and there will be no external force applied to the structure. So this quantity will disappear and this quantity will disappear. So finally, you'll have this quantity left out. Now we have to solve this expression to get our mode shapes and the time period. So we have to little bit simplify this one. What we have to do is, as you see, I told this is a matrix, because means it has n number of modes. So I'll simplify, consider n degrees of freedom. So my deformation vector is the summation of mode shape and modal deformation. As you see, as you have seen in the previous slide, I have just included this summation because we have already seen that we are adding this, although using modal superposition method. So now, if I consider nth mode, I can write the same expression. I can write un is equal to mode shape multiplied by qn, means the deformation parameter of nth mode. And substituting this in my this expression, I get something similar to this one. M, instead of u double dot, I am just double differentiating this one, this deformation quantity. So if you differentiate this 2 times, you'll get the acceleration. So that's why I can write phi is a constant parameter, so it will not have any effect when you are differentiating. So you'll have pi multiplied by q double dot if you are double differentiating this one. Then plus k into u. So instead of u, you can write pi into q. So again, now this is my final expression. If you go to the solution, if you solve this expression, you can refer any standard book for structural dynamics, how to solve this expression, you can get the result. Okay. So if you solve the expression here, you get the result like that. So this is my response quantity which I have to determine. So it will be like that: Q is equal to some constant into cos omega t plus another constant into sine omega t. So this is the result for this solution. Now, since I need the acceleration here, I have to again double differentiate this expression. So I'll get something like that: minus an omega n square, because this omega n is again a constant parameter. So it will come out, and I'm doing 2 times, that's why it is square. And cos omega n t minus bn omega n square sine omega n t. You can just solve this one, differentiate it 2 times, you'll get this. Then this I'll replace, means I'll substitute in this equation. Q double dash will be replaced by this one, and Q will be replaced by this one. So if I do this one, finally I'll get this one. Then you simplify, just an cos omega n t plus bn sin omega n t will be available on both the terms. So you can just take it out as a common, then you can leave it. So if I do this one, finally I'll have this parameter k minus m omega n square multiplied by the mode shape vector. Okay. So in this equation, phi represents the mode shape vector for the particular mode what I have considered nth mode. Then mode shape parameters are real quantity and they are not zero. Okay. So as you have seen, when we have just presented the deformation shapes, it was not zero. Some values will be there, so it will not be zero. So I can say this quantity is zero. If this is not zero, this quantity should be zero if you want to satisfy this equilibrium condition. So what I can say is the determinant of, because this is a matrix form, I have to write determinant of this quantity as zero. So now this is the final expression which you can solve to determine your mode shapes and time periods. Your mode shapes will be this one, and the time periods will be given by this omega. Omega will actually directly give you the frequency, but you can formulate frequency in terms of period also. So these are the 2 parameters we have to identify by solving this expression. First, we'll solve this expression, then we'll determine omega n, then omega n will substitute here, then we'll determine phi. Okay. So either you can solve this one manually. There are a lot of techniques to solve matrix manually. Simply simplified one, which is the most simple to solve but lengthy, is Gauss elimination method. You can apply Gauss elimination method and solve this matrix manually. So if you are interested, otherwise you can take help of optimization software like MATLAB or something similar to like that. You can solve this expression in MATLAB also. Now we'll see how to solve this manually, and manually means I'll not show you the detailed step. You can go to the Gauss elimination method or some other method, then solve manually. I'll show each parameter for a example building like K matrix, how to determine K matrix, how to determine M matrix, then formulate the expression. Then finally we'll find out the result using MATLAB. Okay, that will do. So these things already we have discussed. First, you determine omega n from this expression, then substitute each of the omega n in this, then determine mode shape for this respective omega n. So equation 4 can be solved in MATLAB using eigenvalue solution. So these things, what we do here, this we call as the eigenvalue solution. Means this problem is the eigenvalue problem. Standard form, means standard term we use for this kind of solution is the eigenvalue problem. So this is a example building. I have just shown one frame of this building. Similarly, you have multiple frames. So just for the interpretation. So 4-story building, single bay. This is just for the example, because if I take a complex structure with multiple stories and multiple bays, I will not be able to explain here theoretically. It will be very complex. Here also you see this is just a single bay structure, and um, you have total 8 nodes, and 8 into 6 total 48 degrees of freedom. If I take actual degrees of freedom in each node, so your matrix will become 48 by 48, which is very difficult to interpret here. Similarly, you can imagine if I take actual structure, how much will be the size of the matrix. So it will not be useful to understand the concept. That's why I have taken a simplified form. But if you understand this concept, same thing you can apply for your actual structure. So now say this is a 2D problem. So I have reduced my 6 degrees of freedom into 3 degrees of freedom. I have one translation in lateral direction, one translation in vertical direction, then rotation. So for each degrees of freedom, now I have total 24 degrees of freedom in this structure. So again, 24 degrees of freedom is also difficult to solve manually. So what I did is I have just considered the lateral degrees of freedom, means only story deformations I am considering, other degrees of freedoms are ignored. So in this way, I can reduce 24 degrees of freedom into just 4. I have 1 degree of freedom here, then one here, one here, one here. This is just to understand theoretically. The same concept you can apply in your actual structure also. That you can solve using software like MATLAB, as I said. I'll show the procedure. You can apply the same procedure. So now, this is my structure. I have 4 degrees of freedom. So I have 4 stiffness also. In each story, I consider stiffness of a story instead of stiffness of a particular column. So I'll have story stiffness K1. This is the summation of stiffness of this column and stiffness of this column. Then story stiffness K2, which will be summation of this and this, and stiffness of K3 means story 3, which is this plus this, and stiffness of top story, which is this plus this. Okay. So this in terms of matrix, you can, okay, before going to matrix, this is the same thing what I did here. The same thing I have modeled in software also, just to compare the result, what is given by the theoretical calculation and what is given by the software. So this condition I have simulated in the software. As you can see, in each story, I have just 1 degrees of freedom active. Remaining all the degrees of freedoms are logged. So same thing I have modeled in the software. So this joint you can see, and if you see the degrees of freedom of joint, here you see UX restraint no, means I have considered only the deformation in X direction. All the other deformations you can see restraint, means I have logged. So virtually each of the stories will have only lateral deformations, which is similar to what we have done here. So what I'll do, I'll calculate the time period and mode steps using this interpretation manually. Then I'll also get from the software, and we'll compare both whether they are matching or not. So if you understand this concept, same concept you apply for your actual structure. Same things will be applicable and same result you will get. So let us formulate our mass matrix. Since we have only 1 degrees of freedom, only 1 degrees of freedom, all other degrees of freedoms will be 0. So your mass matrix will be diagonal. Off diagonal terms will be 0 because just 1 degrees of freedom. Okay. And I have taken some particular load quantity and calculated the floor mass, and I got this much. This is for floor mass of first story, floor mass of second story, floor mass of third story, and floor mass of fourth story in terms of ton. Then if you want to interpret this one, just considering only lateral deformation, what I am assuming is my floor is rigid. So this floor, what you can see here, this will be rigid. It will not have any other deformations. It will not have rotation. It will not have vertical deformation also. So that's why EI of beam in the computer model I have considered infinite. Then the stiffness, because here I have considered only lateral stiffness, which is also called as shear stiffness. I am not considering the flexural stiffness here. It has, as you can see here, it has only shear deformation here. So I have to consider the shear stiffness of my story, which is for this particular condition. This is applicable 12 EI by L cube. This is applicable only for this condition, not for your actual structure. I'll tell you a little bit later what for actual structure. So if you have this configuration when only lateral deformation is applied, then you have the stiffness quantity as 12 VI by L cube. And in my model, I have total 4 columns. So I have to add the stiffness of all 4. So 4 into 12 VI by L cube, I am getting this quantity. So now if I formulate the stiffness matrix, this by solving the mass spring system, this again we have discussed in our previous course. Whoever is not referred, you can refer our previous course to get how to get this stiffness matrix. Okay. So you just substitute here the values. Stiffness for all the stories will be same, considering you have the same member sizes. So you just substitute here, K1 will be this, K2, K3, K4, everything will be this because I have same member sizes and length of member. So finally you get this. So now you see I have my mass matrix, then I have my stiffness matrix. So what I have to do is just to solve this expression. And you now know the stiffness matrix and mass matrix. So omega n is the only unknown parameter. So you solve this matrix and get your result. So either you solve manually using some matrix solution method like Gauss elimination method, the simplest one, or you use MATLAB or something similar kind of software. Okay. So here in the MATLAB, what I did is I have written my stiffness matrix. You have first column of stiffness matrix, then second column of your stiffness matrix, then third column of your stiffness matrix, then fourth column of your, first row, not column. This is first row of your stiffness matrix. This is second row, third row, fourth row. Similarly, you have first row of mass matrix, second row, third row, fourth row, like that. Then I have just automated little bit instead of going for details. Some parameter A is equal to K by M. So this you can understand from this expression. If you take out this quantity to the other side, it will become K is equal to M omega square. So you can say omega square is equal to K by M. The same thing I did here, K by M. So now you have to solve. MATLAB already has the automation for finding the eigenvalues and eigenvectors. You can either use that automation technique or you can go for manual solution. Okay, so I have gone for the automation technique. I have first quantity will give you the frequency and second quantity will give you the means first quantity will be the eigenvalue. Eigenvalue means frequency in this aspect when we are solving for a structure. Okay, and eigenvector, the second quantity is the eigenvector, which is nothing but mode shape in case of structure. So this is solved as EIG. This is the command you have to give, EIG of this, whatever you have calculated here. After that, you can extract what is your frequency and what is your mode shapes. Okay, so if you do this, then you get this. This is your matrix for frequency. The term was omega square actually. So you get this only diagonal terms, or off diagonal terms are 0 because we have logged all the other degrees of freedom. So in
Uh, Hello, sir.
Not
It's
audible.
not audible.
am I audible?
Yeah, now
Yes,
it's
Hello.
sir.
audible.
Yes, sir. Now audible.
Okay. So previous slide you have heard, right? This one.
Yeah.
Yeah, you can continue with the next slide.
Okay. So you get the frequency matrix, then convert this frequency matrix into time period using the formula omega square is equal to 2 pi by t. 1 minute. So in this way, you get your time period. I have total 4 degrees of freedom, so I'll have total 4 time periods. So from this, if you convert to time period, you get this. From this, if you convert to time period, you get this. From this, you get this. And from this, you get this. So this is using manual calculation just by solving the eigenvalue problem. And this will now compare with whatever you got from the software ETAB. So I have just extracted the time period values here. The first period is 0.86, second period is 0.3, third period is 0.2, and fourth period is 0.17. This now you can compare with manual calculation, almost same values, just little bit fractional difference. Okay, this also happens because of some parameters which I have not considered in the software. Otherwise, you might have got the same result exactly what you got from manual calculations. Okay, those are not important to discuss, so I'll leave. Okay. So similarly, you get the mode shapes from manual calculation. This is the mode shape matrix for from solving the eigenvalue problem, and this is the mode shape matrix obtained from ETABS. Now here you can see little difference, but don't worry about this one. As I told, in mode shapes, only patterns and shape matters, not the actual values. Okay, and which side it is, that also doesn't matter. So you just compare whether your shape is same, whether your pattern is same. So this I'll plot in terms of XY plot, there you'll understand better. So this is the mode shape plot from ETABS, and this is the mode shape plot from manual calculation. So we'll go one by one. This is the first mode from ETAB, and this is the first mode from software. So there is a little bit difference in the shape, although it doesn't matter because it is in the same side of your axis, not changing the direction. So it satisfies the condition. Okay. Then you see the second mode, which is given by orange line here. This is almost matching the pattern in both the cases. Then go to the third mode, which is given by the gray line here. This also almost matching the shape. You can say entirely, almost entirely matching. Then you have fourth mode, which is also matching. So you can see the same mode shape we get from the software as well as from the manual calculation. And the time period also, whatever you got, we have just written as a comparison table here. You can see. So this is the way you can verify your computer model if you have some doubt with the modeling, whether you have done it correctly or not. So now this was for a simplified model. What you have to do for actual structure? An actual structure, you have to consider all the degrees of freedom. So each node will have 6 degrees of freedom, and this simplified model will not be applicable there. And also here, the locked degrees of freedom should not be applied. All the degrees of freedom should be unrestrained. Okay. And you have any kind of structure with any number of stories, any number of bays, the same concept will be applicable, but this parameter will not be 12 EI by L cube. If you do this one, take actual structure, then apply 12 EI by L cube, your result will be wrong, because in that case your stiffness will be different. And to get that stiffness matrix, you can refer some standard books in dynamics or finite element method. There it will be explained how to get the stiffness matrix. Or else if you are interested, you can attend our upcoming finite element course. There we'll show how to get the actual stiffness matrix of structure. Okay, so those concepts you can apply here. After that, once you get, and one more thing, this mass matrix will also be different. This will not be diagonal. All the off diagonal terms will be available when you consider your actual structure. And again, this will not be simple applying the floor mass. Floor mass here we have applied because we have only 1 degrees of freedom. But if you have multiple degrees of freedom, then quantity will be different, and that you have to calculate. And that is called consistent mass matrix. So we will also discuss consistent mass matrix. If you're interested, you can refer that course, upcoming finite element course. And once you get mass matrix and stiffness matrix, then apply the same rule, whatever we have done here, and you will get the frequency and mode shape parameters. So this is what you have to do in case of actual structure. Okay. So I guess this much was clear. What is the actual meaning of mode shapes? What is the meaning of time periods? what is the importance of those parameters, and how to get these using manual calculations. So this is what we had up to means for the mode shapes and time period. And these are some deflected shape obtained from the ETAP software for the model what we have shown. So this is first mode deformation, second mode deformation, third mode deformation, and fourth mode deformation. Okay. Let us now start with the torsional irregularities. Just give me 1 minute. Okay, so torsional irregularities means your structure will have rotation about the vertical axis. Now, how this rotation happens, it can be because of different reasons. Those reasons we called as irregularities. The rotation about vertical axis is called as torsion, and the reason because of which this torsion occurs is known as irregularities. Okay. Now, if you refer any codal provisions, for example, I have referred here IS1893 Part 1 2016. In table 5, it gives when you have delta max of any floor more than 1.5 times of delta mean of the floor. For example, if you have the floor plan like this, in one side you have deformation, let's say delta minimum, and another side you have deformation, let's say delta maximum. So if this maximum deformation quantity is more than 1.5 times the minimum quantity, then we say your structure is having significant torsion. It doesn't mean that if this is less than 1.5, you do not have torsion. You have torsion, but that is not considered as a significant quantity from the design point of view. So you can continue with your structure. That is what it means. Don't interpret it like that. If you have quantity less than 1.5, your structure is not having torsion. There is nothing like that. So this is one condition to satisfy the torsional irregularities as per code. Then another condition is the natural period of torsional mode should be more than the natural period of your fundamental translational modes. If these are the two conditions, then you'll say your structure is having significant torsion. Either of the condition if satisfied, either first condition can be satisfied or second conditions can be satisfied or both can be satisfied. In all the ways, you have to consider torsional irregularities. So if these are the conditions, then what code says what you should do. If suppose you have 2 times delta mean, means twice of this deformation is more than this, but this deformation is 1.5 more than 1.5 times this. So if the range is within this limit, then you have to revise and satisfy the condition, or you have to go for 3D nonlinear dynamic analysis. It means nonlinear time history analysis. You have to, not the linear time history analysis. Usually when people design the building, sometimes people use the linear time history analysis, but in this condition you have to go for 3D nonlinear time history analysis. Okay, if this is the condition. But if suppose your condition is like that, delta max is more than 2 times delta mean, so this quantity will be more than twice this. In that case, you have to reject your model. You cannot carry on with this model. You have to revise that. There is no other condition as per code. Although this condition is actually modified a little bit in our draft code, you can refer the respective clause. So this condition is a little bit relaxed, you can say. Instead of applying for 1.5, they have given some higher values like that. So this is as per codal provisions, what you have to do to satisfy the condition as per code. But as I said, it doesn't mean there is no torsion if this is the condition. Let's say delta max is less than 1.5 into delta mean. So there will be torsion. Now, if you are interested in avoiding torsion, what you can do from the modeling point of view, that is what the objective of further discussion. So a well-proportioned configuration balancing the lateral stiffness distribution in plan according to the mass distribution at each floor. If you can do this one, you can satisfy the torsion, means you can avoid torsion, although not completely, but you can minimize up to a good extent, I can say. Then as per code, this is the condition you have to do. The aspect ratio of floor should be less than 3 to avoid torsion. So this is codal provision. Now let us understand how torsion occurs in your structure. After that only we'll be able to understand how to eliminate torsion. So let's say this is one floor plan, and I have total 4 vertical members located at 4 corners, which will be resisting my lateral forces. So let us also assume this is the center of mass, and this is my center of stiffness, depending on the stiffness provided by these 4 vertical columns. So the eccentricity is the distance between center of mass and center of stiffness. Here I have shown only one eccentricity in x direction. Similarly, you will have this direction also. So you'll have two eccentricities actually, x direction distance and y direction distance. But just for the interpretation, let us consider this as the eccentricity. So what will happen? Your earthquake force or any lateral force, this will be applied through the center of mass. So this is my input force or applied force, but your resistance will be applied through the center of rigidity or center of stiffness. So now you can see from the equilibrium, if you satisfy the force equilibrium condition, the the force applied should be equal to the resisting force. That means your resisting member will provide the resistance equal to applied force. So this both the forces will be equal. Now two equal forces are applied in opposite direction with some lever arm. This eccentricity now you can say lever arm. Okay, so what will happen? It will generate a couple like this, some rotational movement. So you can just visualize it is this force is trying to push your structure in upward direction, but this resisting force is trying to push the structure, same structure, in the downward direction. So it will start rotating. So now if you want to eliminate this rotation, what you have to do, this center of mass and the center of rigidity should be brought as much as close to each other. If you are reducing the distance, the rotational moment quantity will be reduced. So this is what you have to do. Try to bring these both the centers as close to each other as possible. Okay, so you can say if center of mass and center of rigidity coincides, there will be no torsion. Then this how you can achieve is by appropriate distribution of resisting members. Randomly providing your columns at any locations will not provide you this advantage of elimination. You have to decide it wisely where to provide which member. So this you have to do. And the preferable way from center is always away from the center towards the periphery if possible. I know there is a lot of limitations for a practicing engineers to implement this clause, uh, providing lateral resisting system away from the center of mass. I know these limitations, but still wherever you have scope, you can try to do this one to eliminate or to minimize at least the torsional quantity. Okay, then this procedure is going to be iterative. It means you cannot try for one times and achieve this elimination. You have to do it multiple times based on the observation from each trial. Suppose you are doing some iterations and you are not achieving, but you are changing some um, you are observing some changes in the parameters. So based on this observation, you can identify in the next trial what you have to do, which quantity should be changed. Like that you'll be able to identify. So now the movement, torsional movement, will understand how these members are resisting this torsional movement, and then only will be able to understand what to do next. So let us say the torsional moment is m theta, which is created by this couple, although actually direction is opposite. Here it should be in this direction, clockwise direction, but by mistake I have drawn it anti-clockwise, but leave it, it doesn't matter. So according to this anti-clockwise direction only, we'll discuss these remaining terms. So let's say this is the torsional moment applied by the couple created by the center of mass and center of rigidity. Now what the structure will do, structure will try to resist this torsional moment in terms of resisting stiffness of vertical members. So if your applied moment is in this direction, your resisting moment should be opposite to this direction. So if you want to achieve this one, your member should act like that. Your x lateral stiffness will be applied in this direction for this column, then again same direction for this column. But for the other two members, the x direction stiffness should be in opposite direction to create an opposite rotational phenomena, you can say. Similarly, if you see the vertical stiffness, to create a clockwise movement which is opposite to the applied movement, so to create a clockwise movement, the vertical stiffness of this member should be in upward direction and vertical stiffness of this member should be in the downward direction. Okay, so now you can calculate the opposite moment with respect to any point, let's say with respect to center of mass. Let's say I consider the first column and calculate the moment, because means resisting moment because of this column about center of mass. So what I have to do, I have to convert this stiffness into a force, then multiply this force with the displacement. Okay, so this stiffness when multiplied with the displacement will give you the force. So how much displacement is occurring because of this rotation? You can say if this angle of rotation is theta because of this applied moment, then let's say I want to find the displacement at this point for this column. So what will be this? Theta multiplied by this distance. So this will give me the displacement at this point. Similarly, you can calculate displacement at any point, either at this column, either at this column, or at this column. I have just shown here for one of the sides. Similarly, you can consider for all the sides. Okay, so going by this concept, if you want to calculate the stiffness because of this moment because of this x stiffness, what you have to do, you take this x stiffness, then displacement of this column in x direction, then multiplied by uh, perpendicular distance up to this center of mass. Okay, so now if you want to calculate the displacement in x direction for this column, what you have to do, theta, if you take theta in this direction, it will be same as this theta because diaphragm is rigid, which is assumed here. So this theta multiplied by this distance will give you the horizontal displacement. So that means theta into this distance, I can say d1. So that is why I can write the moment because of this x stiffness is k1x multiplied by theta into d1, which will give me the horizontal displacement, then multiplied by the perpendicular distance, which is nothing but d1. Okay. Similarly, you can calculate for all the other members. For second, this is the second one. So moment because of x stiffness, k2x into theta into d2. This will give you the horizontal displacement multiplied by the perpendicular distance, and so on. Same thing you can do for vertical stiffness also. So I have total eight stiffness parameters here, 4 in x direction and 4 in y direction. So if you solve, means sum up all these 8 stiffness parameters to get the moments, you can write m theta is equal to, means applied moment is equal to sum of resisting moment by each of the columns in each of the directions. Okay, then you simplify this one. Theta is common in all the terms, so take it out, and d is also coming 2 times, so you can say d square, and this d is coming for x stiffness according to this definition here, and for y stiffness b will come. If you solve this one, you will get to know how this b is coming. So you have the expression, final expression, similar to this one. Then my objective is to determine theta. So what I can do is I can keep theta and remaining terms I can take to the other side. So you'll get m theta divided by this stiffness terms. Okay, now here you see. So theta is equal to applied torsional moment divided by sum of the resisting moments. So stiffness multiplied by distance square. And all the members are added together. Similarly, if you have actual structure which will have lot of higher number of members, so you will add all this here. Then you can determine, because of the eccentricity, how much rotation is occurring in your structure. So once you identify this rotation, your objective should be to minimize that rotation. Okay, so this is what we have to do to minimize this rotation as much as possible. So now if you look at this expression more carefully, there are a lot of insights you have to understand. Okay, how many different ways you can control this rotation. So let's start from this numerator value m theta. So this theta can be reduced if I can reduce this m theta. So how we can reduce m theta? That is not direct, that is indirect. So I cannot directly control this one. Okay, but these things I can control because this is the applied moment, and it depends on the inertia and the effect of earthquake. So there is not that much control I have in this parameter, but I have control in these all parameters. So what I can do, I can increase the stiffness of all the members, then I can increase this distance, all the distance. So that is what I just in the previous slide told you. Increasing the distance away from the center will have maximum effect. This you can understand from this expression itself. If suppose you are increasing the stiffness, your effectiveness will be just 100%. But if you are increasing the distance, your effectiveness is exponential, square times. Okay, for example, you initially your member distance from the center of mass was 100 mm. Now your member is at a distance of 200 mm. So for the same stiffness, without changing the member size, it will give you the twice effectiveness in resisting the torsion. So this is what you can understand from this. So that's why I always say, as much as possible, try to locate your member as away from the center as possible. If you are not willing to increase the stiffness, because increasing the stiffness will have less effectiveness, so it is better to locate it away from the center instead of increasing the stiffness at closer distance. Okay, so finally what you can say is this rotation is proportional to some kind of function of inverse of distance in one direction square, or and inverse of distance in another direction, means square, inverse of square of the distance. So from this expression only you can identify what you have to do to minimize the torsion. Increase the distance of vertical resisting member as much as possible. Wherever you it is possible, you try to do that. It will have a lot of effectiveness in saving the materials also, because if you are increasing the stiffness, you are increasing the cost of your structure, as well as effectiveness is not that much. Okay, so doing this one you can save the materials also. So torsional rotation, this is the objective, need to be minimized. As I said, the less efforts are needed if more stiffness are distributed in the periphery. The effect is exponential, as I told here. Then lower member sizes and materials needed. If you are following this second option, you will need less member sizes and less materials for giving higher resistance. So ultimately your structure is going to have cost advantage. So this is what you have to do. Then indirectly in software, when you are checking, you have to check the center of rigidity in x direction and in y direction, because rotation, I don't know whether software directly gives it, I didn't check it. if the software is giving rotation, then it is fine, better to check the rotation instead of checking the distance of eccentricity. I'll tell why the checking of eccentricity is not recommended. Instead of that one, you look for rotation. This I'll explain a little bit later why it is so. So this you can calculate. If you are interested in calculating center of rigidity in x direction, this is the formula you have to apply. Stiffness in y direction multiplied by the perpendicular distance for all the members divided by sum of total stiffness. Similarly, if you are determining the center of rigidity in y direction, so you have to consider stiffness in x direction multiplied by the perpendicular distance. So this is because of this effect what we have discussed here. When you are calculating the x stiffness, you are multiplying y distance, and when you are checking y stiffness, you are determining you are referring x distance. So because of this one, these things happens here. So in this way you can calculate the center of rigidity in x and y direction, and you can compare with center of mass and center of rigidity. If both are matching, then you can say there is no torsion, but this will not work all the time. So that is why you have to go for rotation, not center of rigidity, means eccentricity. I'll explain in the last slide why it is what I'm telling here, what is the reason behind that. Okay, so this was the theoretical concept, what you need to understand to eliminate the torsion. Now let us see some examples. What I have presented means I have tried to eliminate the torsion, and the procedure, as I told already, it was iterative, so you have to do some iteration. But number of iterations will be less if you are focusing on the peripheral members. It will be more number of iterations, and the effect you can relate with this one. If you are focusing on internal members, you have to do the iteration twice, not twice, square times from when you are concentrating on the peripheral members. So that is also a factor you have to understand. So it is better to focus on the peripheral members, so you have to do less number of iterations. So this is our first example. This is a 20-story frame moment frame building, and it has plan irregularity, as you can see here, but there is no vertical irregularity. So the floor plan is same for all the stories. Then when I determine the mode shapes and time periods, this is what I got. In the first mode, this is the time period, although time period is not important for discussion, so leave it. Sorry, this is important to understand which time period is higher. So let us discuss this also. So this is the time period, and this is the mode participation factor, mass participation factor in the x direction, and this is in y direction, this is in z direction. So you can say the first mode is torsional because torsional contribution is higher, and also the x direction means translational direction contribution is less than 65% or less than even 50%. So this is a pure torsional mode, and this is how it looks when you see the deformed shape. Okay, this is a plan view, so you can see only the plan here. Then in the second mode, this is translational mode, we can say. If your participation factor in a particular mode is more than 75, we consider it as a pure translation mode. Okay, so this is almost 75, so you can say pure translation mode, but first mode is torsional. Then third mode is, uh, although the participation factor in x is more, but it is not sufficient, you have significant quantity in torsion also, so we can say this is mixed mode. If this participation exceeds more than 65, then you can say at least acceptable. This is a translational mode that you can say. Okay, so this is for original structure. I didn't do any improvement here. Just take I have taken some uh, configuration of the structure, then determine, and this is how it looks. Now my objective is to improve this structure to achieve translational mode. In one direction it is already available, I have to fix the other direction. So I did some iterations, and I have okay, before that, if you want to see the center of mass and center of rigidity, so it is giving, and I determine the eccentricity. So eccentricity is nothing but the difference between center of mass and center of rigidity, so that you can calculate for x as well as for y. Okay, so this you get here. Then I tried to improve the structure, and this is what I did. It may not be real type of configuration, just to show you. So I changed the stiffness of my peripheral members. Just corner members I have changed. And actually, it was not a single iteration. I did some 3-4 times. After that, I reached this final configuration where condition was satisfied. So what I did, and I didn't change any floor configuration, means floor plan configuration. Then shear walls are located. Earlier it was a moment frame building. Then now I have introduced shear walls in the peripheral members, some of the peripheral members. Then deciding shear wall, when you are locating shear walls, what know-how you have, some initial knowledge you have to locate the shear wall, where you have to have, means where you have to look at. So the know-how we have learned in the previous slide is as away from the center as possible. So the same concept I have applied. There is no other thing you can say. If you are looking to introduce the shear wall closer to the, suppose your center of mass is here, you are introducing shear wall here. It will not have that much effect. So I have done means followed that point as away from the center as possible, and following this one I have introduced this shear walls. Then in the iteration process, before reaching this final configuration, what I did, after each iteration I have checked the modal behavior and eccentricities. So if this was not satisfied, then I went for the next iteration. This is what I followed there. So two conditions I followed. One is trying to locate the members as away from the center as possible, and checking the modal response after each iteration. So procedure continued until the satisfactory behavior observed. So once your condition is satisfied, then this is what I got. Although by checking the mode steps, you can say this is not pure translational mode in X direction, but if you check the quantities, mathematical quantities, in X direction participation is more than 65, so this is acceptable. Then in Y
Sir,
direction, yes, yes,
you have written in first mode that translation with acceptable torsion. Sir, what should be that limit we can accept torsion? Sir, in first mode, as we have learnt through our course, that we must not
hmm,
allow torsion in first and second modes,
hmm,
no, sir.
yes, yes.
But
So
you are
here
getting
it is.
9.6.
Yes, I got your point. See, these two terms are relative. This translational participation and rotational participations are relative. If one quantity is increasing, automatically another quantity will decrease. Okay. So your objective is to satisfy this more than 65. So if more than if this quantity is more than 65, this will be automatically less. It will reduce. Okay. So you don't
Where is
have to.
where is 1 minute? Sorry to interrupt. Where it is given 65% has to be achieved?
Sir, that we'll discuss after the session. Let me first
Okay,
complete. Okay.
okay, thank you.
So you
Okay,
just
so
take.
Rajul, so I would
Yes.
like to introduce Mr. Prasanna Kumar. He is
Hmm,
representing from the industry in the session today. Okay, so
hmm,
we will discuss on this point with him. So he is a
hmm,
director in one of the companies and mostly
hmm, hmm.
high-rise buildings. He's
Yeah.
doing that. So what are the
Hmm,
challenges faced? We will discuss
hmm.
one-to-one with him after this.
Yes, yes. Actually, I know him. He is also participated in our last
Yeah, yeah.
course on performance-based design. So I already know him very well. Yeah. And sometimes we also have the discussion also, right, sir?
Yes.
Yes. Okay. So we'll discuss this later on the means after the session. We can discuss. Okay, fine. So you just take care of this translational mode. Rotational mode will be automatically reduced. Okay. So if this is more than 65, you accept this, otherwise try to improve this one. Then in the second mode, it is satisfied. In the third mode, you can see this is torsional. So this is what we have to achieve. First two modes should be translational, and third mode will be automatically rotational. Okay, so this is our objective. So doing this improvement, I could achieve this one by doing some iterations. So this is one example. Then let us also discuss our next example, which is a very ugly looking building. Okay, again, before going to that one, you can calculate the eccentricities and compare this with the eccentricities obtained previously. So here you can just compare this whether it has actually reduced or not. For example, if I see X parameter, you just have a observation here relatively how much is the range here, 0.1 to 0.28. Then if I compare this with this one, it is going from 0.0022 up to 0.52. Somewhere it is reduced, somewhere it is increased. Similar things happens in case of y direction also. So that is why I told you it is not always preferable to look at these eccentricity parameters. You have to look at the rotation. And when I present another two observations, and after that one explanation for this, why it is happening, that also I'll give, you'll understand it more clearly, why it happens. So always try to look at the rotation, not the eccentricity displacement parameter. Okay, so this is the ugly looking building, what I was telling. I just wanted to get some irregular shapes, so took it. So the next building will be very interesting. So don't worry, that will be realistic building that we can discuss. Okay, so before going to that one, let us discuss this. This is also a 20-story building, movement frame configuration. And after doing the model and same thing, we have plan irregularity, but no vertical irregularity. So modal analysis results are like that. You have, although first mode, although I took irregularities, but still it was giving me translational mode in the X direction. It my bad luck. Okay, so second mode is torsional. You can say you can see here X direction contribution is only 40% and Y direction is almost similar range, 30%. Then third mode is expected torsional. So now again I have to improve this structure, and before going to that, again you have eccentricity parameters calculated here. And in this case, you'll see when we'll present the eccentricity parameters from the improved structure, it will be seeing eccentricity in fact increased in the improved structure. Okay, so that we'll discuss there where I present that table. Now, this is the improved version of the structure. I have introduced some shear walls, and here we have opening. Okay, below this wall, I have opening of 2 meter by 2 meter to provide the passage here also and here also. Okay, so this is the improved version, and here this is the final modal response we have obtained. 68% in X direction in the first mode, and 65% in the Y direction in the second mode, and torsional mode in the third direction. So condition is satisfied, you can see. Okay, and then these are the response, eccentricity parameters. Now you see Y direction will be more clear to understand because of the higher difference. You can see eccentricity in Y direction is 1.37 meter at this floor. And this, if you compare with the previous one, here I have only 0.58. Similarly, there is no quantity which is more than 1 here. But if you see, the improved structure is giving you more eccentricity, in fact, compared to the original structure, which was not torsionally satisfied. So what I mean to say here, if you are relying on reducing the eccentricity parameter, you may not reach your final configuration at all, because this is not a reliable information to check. So here you can see torsionally condition is satisfied, but eccentricity condition is not satisfied. So what you have to do, you have to satisfy the torsional rotation condition and this modal response condition. So torsional rotation is theta, what I have introduced earlier. Okay, So this was about the second example. Then we have this nicely shaped building, the third example. This is a 40-story office building. Here I have plan irregularities and as well as minor vertical irregularities. Although here in this floor the irregularities are available, there are some other floors at two different levels where I have some balconies here like that. Okay, so that is the little bit irregularity introduced here. So this is original configuration. These are the lift core, you can say, or you can even use for staircase. If you're using one for lift case, another one for staircase, so you can do that. So this is the core system giving here, and this is the external elevation of the tower, and this is the modal response outcome. Here you see in the first mode, this is pure torsion. The translational contribution is even less than 10%. Okay. Then in the second mode, you have 14-15% contribution in X direction, then 56% contribution in Y direction. So we can say this is less than 65. So we consider this as a mixed mode response. Then in the third mode, you have 58% in X direction and 15% in Y direction. Then again, we can say this is the mixed mode. So our objective should be to improve this structure to get the translational mode in first two modes. That is what we are going to do. And before going to that one, again, you have the eccentricity calculated here. And then we have the improved structure. This is the final configuration of your improved structure. So what I did, the lift core I have shifted on peripheral side. So two lift core I have shifted here and two lift core I have shifted here, and introduced some other members also. In the iteration process, I did some iterations. So this configuration was reached based on the iteration we did. And finally, I could reach this. So the condition is satisfiable. You can say 67% in X direction, 65% in Y direction. And then third mode is torsional. Okay. So this is what we can do, shifting the primary lateral load resisting systems as away from the center as possible to satisfy the torsional conditions. Okay. Then these are the eccentricities calculated, and again you see this quantity if you compare with this. So in the second case, these are higher. So again, you will not be able to reach your final outcome if you are relying on these parameters. Now let me discuss why this happens, why this checking eccentricity is not giving you the satisfiable result. So for that, you can refer this figure. Let's say in the original structure before improvement, my center of mass was located here and center of stiffness was located here. So this is the X distance eccentricity, and this is the Y distance eccentricity. Okay. And this is your rotation. Then let's say I have done some improvement. There will be no significant changes in the center of mass, although there will be little changes, but not significant, because maximum mass is coming from the floor loads, self weight of slabs, then live loads applied on the floor, and wall loads. Changing the vertical lateral load resisting members will not add significant load to your structure. That's why there will be no significant changes in the location of center of mass. So for this explanation, I have just fixed constant center of mass to give a clear understanding of what I mean. So when improved structure means when I have done the improvement in the structure, let's say my center of rigidity is here. So you can see the eccentricity is increased in fact. And if you see X eccentricity is more than double compared to the Y eccentricity. Similarly, eccentricity for the improved structure is more than double compared to the x eccentricity of the original structure. Similarly, the eccentricity in y direction is also higher for the improved structure. But when you interpret the rotation, you find out the rotation, then you see the rotation in the second structure, means the improved structure is less compared to the original structure. So as your torsional moment will be function of the torsional rotation, not the individual eccentricity parameters. That's why you have to look for the rotation, not the eccentricity parameters. So eccentricity parameters will work only when you match the center of mass and center of rigidity completely, means there is no eccentricity at all, 0 0. Then only that checking eccentricity in x direction and eccentricity in y direction will work. But if you are not able to match both the centers, then it is better to look at the rotation parameter instead of going for the uh, uh, distance parameter. So this is what you have to understand here. So this was all to discuss actually, and I hope whatever you have discussed here is clear. And now we can discuss if you have anyone is having doubt. And before going to that discussion, let me show you the mode shape of final structure, how it is behaving in all the modes. So this is X mode shape. And then it is Y mode shape. And then we have torsional mode shape. Okay, so this is what I have. And thank you. Now we can discuss the doubts.
See, coming to the first figure, you improved the this torsional behavior by introducing the shear walls. Correct? First example.
Yes.
First example.
Yes. Yes.
Yeah. See, you introduced the shear walls, you improved the torsional performance of the building. Okay. But in the periphery, can you add the beam element is there? Correct? For the periphery, you will connect the beam element. For beam element, can you use spandrels? Spandrel beam concept. Suppose your beam is 1000 by 600. Same thing can be modeled as a spandrel. That also gives a better torsional resistance. If I model the spandrel beam in the tab, it will the torsional resistance will improve. But that is the correct approach or not? Because many people will use the spandrel beam.
No. Spandrel beam, I think it is applicable only when you have the portion above the floor level, door level. So that I think you can model as a spandrel, not the beam.
But because they're considering this is also stiff, realistic stiff. Spandrel also same. What is exactly the stiffness will be come into picture. Very.
What
Because
design criteria you follow in spandrel?
You will divide the spandrel into fine tuning. Number of segments. Say, suppose 10 meter is there. Every 1 meter will divide it. Spandrel will assign different pier level. The behavior will come a beam only, but stiffness will improve.
Yeah, spandrel is a horizontal member, deep member. It will always help resist the lateral force also. So it is.
But I can make it as a bending behavior by dividing the number of segments. Okay, now if suppose 10 meter is there, I can divide it every 1 meter. I can assign one single pair AD, single spandrel AD. Then the bending moment will come like your normal beam. Flexural behavior.
When you are talking about stiffness and bending moment, it will not depend on your structural element type, whatever you have chosen. If you are relying on that, that is wrong, because load will come from your configuration, not the element type. Okay, so if you are relying on the software using some other element to reduce the moment and reduce the stiffness or increase the moment or stiffness, that is not a good thing to do. Okay.
But it will give improve. You have seen by creating the spandrel, the torsional resistance
is improved. I understood. I understood. What I mean to say is stiffness is a function of cross section and the length of the member. So it should not change irrespective of what element type you use. If it is changing, then there is something to look at the model. Okay, so this is what I mean to say. So you should not rely on the software to virtually change the stiffness, because this is not going to happen in your actual structure. That you have to understand. And why stiffness should not change by changing the element type, that we have little bit discussed in our last course also. And if you need more clarification, we can have a separate session where we can discuss why stiffness should not change by changing the element type.
Okay. But why 60% basis is you are giving for torsional mode?
Okay, 60% actually, see.
Huh?
Yes, I know that 60% is actually a reliable limit. In code, it says that the combination of modal participation from first 3 mode should be 60% at least. Okay.
Correct. 60%,
But based on our experience, what we did, if it is less than 60% in the first mode, you get significant torsion. And your torsional satisfaction means torsional, it is not satisfiable. And if you design the structure, one using the 60% contribution at least in the first mode, and another structure, same structure, but combination of all 3 modes giving 60%, you see the final design parameters, then you will understand why we say that. Okay, there will be changes in the quantity of reinforcement requirements.
Okay.
So that's why it is better. It is better to look at, if possible. I am saying if possible, better to satisfy at least 60% in the fast mode. But you may not all the time satisfy that. That time you consider the condition what is given in code. Try to satisfy at least 65% in the first 3 mode.
Normally, not building configuration. Normally, not possible sometimes. That's why I'm asking.
Yeah. So that's why I'm telling this one. This is the thing. Yes.
Similarly, my question is related to between IS1893 2002 versus 2016. In 2002, there was no clause about 60% contribution first to mode should be translation. So what about the older building, which are still not completing and some floor are still going on? So how about take care of the torsional irregularity? Because building is in going on process, so how can take care between the 2002 versus 2016?
There are 2 aspects you have to understand actually. First aspect is really trying to satisfy the performance of the building, and the second aspect is satisfying the condition given in the code. Because as a structural engineer, second aspect is important for us. Okay, so in the event of failure, if suppose you have designed the building as per 2002 code, but earthquake happened and the structure failed, so your structure will be checked, or in the event of legal when court cases will come, something so on, that time your structure will be checked according to the code which was applicable that time, not the current code. Okay, so if you satisfy the conditions given in the code, then you will be safe. But suppose as a person or as a owner of the building, you want to satisfy your performance, means building performance, then you can try to upgrade according to the current code. So these are the 2 aspects you have to understand.
Legally we can offend by the older code.
Yeah, because that was code given to you, and that is not your opinion. That is given by the code committee, which is the authority to take care of these things. So they have given, you followed and you designed. That is not your fault, even after following all the provision also, if structure is failing.
Yes, in I think in a code 2 things are there. First thing is plan irregularity. Second one is a vertical irregularity. So 1.5 limit, I think when we check first corner to second corner, limit is satisfied sometimes, but torsion torsional board will always show there is some torsion. So how about the 2 condition? What can verify?
That's what I discussed in this slide. When your delta max is more than delta mean, code says your structure is having significant torsion. Okay, but it doesn't mean that when this delta max is less than 1.5, there is no torsion. There is torsion, and that torsion you have to consider in your design. Okay, so what you have to do when this is more than 1.5, either you have to revise or you have to run 3D nonlinear dynamic analysis. But if this delta max is, let's say, more than 1 but less than 1.5, then you have to consider the dynamic component of eccentricity, which is 1.5 into static eccentricity. Okay, so that you have to check.
In between, you're telling 1.5 to 2, you have to consider this eccentricity.
No, in between 1 to 1.5.
In between 1 to 1.5.
In between 1 to 1.5, if this factor is coming, then you have to consider the dynamic component of eccentricity. Okay, but if it is more than 1.5 but less than 2, that time you have two options. One is revise, then satisfy the first condition, or else perform 3D nonlinear dynamic analysis to show that your structure is performing well. So this is when 1.5 to 2. But if your structure is having more than 2, that time there is no option. You have to reject that configuration as per this code. In recent code means draft code, it is different.
I think 3D dynamic dynamic analysis, I think X, Y, and Z direction is quite sufficient. Why nonlinear dynamic analysis is required? Because in India there is no significant rules and regulation was not there. No codal provision also not there. So how can take care the 3D analysis?
So that is fine. We do not have our own code, but there are established codes available like ASCE41, which is very much a widely accepted code for nonlinear analysis throughout the world, not in only in US. Okay, so that you can follow. And the another thing what you have asked, why linear time history analysis is not sufficient. When you are performing linear analysis, you are only getting the forces. You are getting the forces. You are not getting the capacity. Okay.
I think so if we are applying P delta effect and vertical earthquake, X and Y and 3 direction analysis, we are doing in a software, I think is quite sufficient, because this is also a nonlinear analysis.
No, I got your point, but you are mixing two things. So that's why I'm explaining one by one. Let's discuss first thing, which is linear dynamic analysis. Okay.
Yes.
So you analyze the structure using linear time history analysis. So as a outcome, what you get? That is the forces, force demand, what is expected during earthquake. That's what you get, right?
Yes.
So
my question,
in this case,
why we need time history analysis?
Let me complete. So in linear analysis, you are getting the demand, but you are never satisfying or never checking the capacity factor or capacity terms. That's why nonlinear time history analysis comes into picture. Although you have used linear dynamic analysis and you have considered that demand to design your structure, but you have to still check whether your structure is actually capable to take that demand or not. So there nonlinear time history analysis comes into picture. In nonlinear time history analysis, we check the capacity, not the demand. Demand is already done using the design procedure, using the time history, linear time history procedure. The demand is already available in the structure, and we have designed our structure according to that demand using the codal provisions. Then now we have to finally check whether the design what we have done is actually capable to take the demand or not. So that's why you have to go for nonlinear dynamic analysis.
Yeah,
so now you can ask
question. My next question related to time history again. So in India, we have no exact data about the time history. So how can take care of the time history if my building is in Delhi, second building is in Lucknow, third building is Kolkata, and periphery any 100 kilometers locations, data may be vary. So how can take care about the time history data?
Yes, nice. Actually, this question is very much relevant for all the structural engineers. So you have options. Um, there are experts available who does such kind of studies, site-specific studies. Even in our department also we do that one. So you can go to any expert who are willing to give you those time history information for you for the site, what you are intended to do. Then you can they'll do the work and they'll give you the ground motion suitable to that site. That is one thing you can do. Another thing is, if you know the information about the site, like you know the VS30 parameter for the site where you are going to construct your building, then you know the magnitude of expected earthquake. So if you know these parameters, then you can go to peer column database. This is one of the widely used database. Spelling is PEER, peer. Sorry, not column database, peer time history database. So there you input this VS30 and magnitude, and there are some other parameters also they'll ask, but whatever you know, you provide. At least minimum parameters will be VS30 and magnitude. So then the software means website will suggest you a set of database, ground motion data. So those ground motion data you can take and use for your structural analysis. So you have two options.
See, capacity term means you are checking only plastic hinge formations, correct?
Yes, capacity means we are checking the hinge formations and
Hinges
whether the
formation.
load applied is within the acceptable limit or not.
Okay, that should be formed in first columns, then beams, like that. That proportion has to be formed. Not sorry,
Yes,
it has to be formed in beams, then columns.
first
Hinges.
beams in columns, and also your structure should have sufficient ductility.
Okay. See, the whatever given diagram 1893-2016, that is amendment has given 1.2 to 1. New added old one, I think.
Maybe actually this is just for reference. This is just for reference I have taken. So if you take the draft code again, these values will be different.
Yes, correct. So you telling torsion irregularity can be improved by keeping the floor stab stiff, correct?
Yes. No, this is just one thing you can do. You are talking about this one, right?
Yes.
This is just one thing to do, which is suggested in the code. It is not like if you are following this clause, your torsional condition will be satisfied. It's not like that. So that's why I have shown you different options what you can do. So you can try all these options to satisfy the conditions.
See, yes? Problem is you told an office building you introduced core walls and staircase at the center of the away from the building, but it is nearly center of the building. That is nearly center of the building. Okay, na office building. Normally in office building, these are at central locations. They never allow. Only periphery of the building they will allow. Staircases and core walls. Normally regular structures. If I go design it, the core walls and staircase will happen on one side of the building. Okay, na?
Okay, only one side you have core wall, another side you will not have anything.
Another side no nothing. Only beam frame. Flat slab system and beam frame will be there like that.
That is what you need to change.
That kind of configuration will come into picture.
I understand. So I understand. So there are difficulties.
I think initially we have discussed about the spindle, and second one is a bracing. So bracing is a good option if you have an option about.
Yes. If you don't have any options left out, then you can go for energy dissipation device like bracings or dampers.
Yes.
Or even if that is not possible, then you have to either go for nonlinear dynamic analysis or you have to reject that. That are the options available. But actually what happens is in industry, people never follow that one. If that is satisfied, okay. Otherwise, they will leave it and simply design and construct the building. So this is actually very dangerous.
Correct. Now the example 3 you are given, In the example 3 plan irregularity, I'm checking this 1.5 delta maximum, delta minimum. Okay, na? So in the present plan, which one you are taking delta 1 and delta 2? Because the plan is very irregular.
Yes, yes. So what you can do, you can just draw a line, or you can take extreme end. You can take this extreme end and this extreme end, and this extreme end and this extreme end.
No, experiments you have to take. Okay, okay.
Hi, Tazul. Hello.
Hi. Yes.
Yeah, hi. So for an office building, it is okay. And if you have a residential with a large basement area, so and we have an individual towers of around 15 to 20 towers, which is around each tower is having only 10 meters by 3 meters, right? So those are all connected by a single corridor.
Okay.
So in that case, how these torsional irregularities will check for the each and every tower?
So tower is like you have individual tower, and at certain level corridors are provided to connect those towers.
Yes.
Correct.
So you can the easiest way is to split the towers in the corridor level, like cantilever type corridor. You can provide half from this tower, half from another tower. Split it.
Okay.
Practically, it is not acceptable by the developers.
No, this is the easiest thing to do. I don't know why they will not accept, because from outside,
No, leakage
suppose,
problems, cantilever means expensive giant will create, no? Expensive giant will create. Again, that is creates a leakage problem, for serviceability point of view, they will not accept it.
Okay.
Yes.
Yeah, maybe different restrictions are there. Otherwise, what you have to do, you have to go for dynamic analysis and check.
Yeah, but I'm not familiar with E-types, but instead we'll model it as a one model. But the whatever we are getting the mass participation factors, and these are for the entire block, right?
Yes. So that is not acceptable for whatever configuration you have introduced, like corridor connecting multiple towers. If you are modeling one tower, you are ignoring the significant torsion, because torsion will happen because of that only. So you are completely ignoring that. So that is, I don't think it is recommended. In fact, that is most important to consider in your case. We can somehow ignore if this is the configuration, whatever. Yes.
Yeah, Mr. Mohan, can you just elaborate on the problem that let's say there are three buildings connected by a common basement or podium, right?
Right.
And is it above ground or it is below ground?
Above floor.
Above ground, right? Above ground, right? It is a common podium which is connecting the three buildings.
Yes. Actually, it's a single. It's a single building.
No,
but it has a multiple towers.
No, I think, sir, I think I have missed one point here. Whether it is podium building or corridor at higher level connecting the floors.
Higher levels is talking.
Yes.
Okay. So that's what I have told that you can follow.
So how it is leading to torsion? That is the first question. That connecting on the higher tower, how it is leading to torsion? That is the first question. That what is leading to torsion in that case?
Okay. That I think. Let me open that last. Sorry, not last. So what you can see here is, yes.
Sorry, I have added a typical plan screenshot in the WhatsApp group.
Okay.
Sir,
which group?
So,
chat also you can
okay.
keep it here.
Okay.
So,
in chat. One second.
Hello.
Yes, sir.
Yeah, I can see your post here.
Right.
So
it is a
you have
type tower, right?
Yeah. So it's a 3 basements, and 3 basements are in the ground only, and the above there are from the still floor, there are individual towers.
So that stiffness distribution above the ground level has to be considered, or at the level where your podium is getting end. Okay. At that portion, you will consider the building, okay, not below that. So how torsion will generate, that is still my question to you. Why torsion is generating?
Torsion at the upper level. That is your question, right?
Yes, right, right.
Okay. So let me introduce this building here. 1 minute.
I mean, how do I identify the whether this individual tower is affecting for the torsional?
Let us try to understand. Let us try to understand. 1 minute. So what you have is
Can you
something
paste the
similar to this.
pictures from the WhatsApp group here so all can see that image?
1 minute.
ಎರಡಾಗಿದೆ. Kind of buildings will normally come into many people's will face.
Okay, so this is your structure, and what this block represent? Each block one tower or something?
Yeah, each block is one tower.
Okay,
Not
so
one tower,
these towers.
One block, one 2 BHK, 3 BHK flat like that.
Yeah, each block is a 1 BHK. I mean, one flat.
Okay, one flat. And what is tower? This one is one tower.
Yeah.
Yes.
And this is another tower, and this is another tower. So 3 towers.
Yes, right.
Okay, at level above the podium, these towers are individual but connected with corridor at certain level.
Yes. No, each level corridor is there.
Okay, at each level corridor. Okay, fine. So I can see this is the corridor, right?
Yes.
Okay.
But I don't think code is allowing this type of arrangement to happen. You have to.
Yeah, code is not allowing. Code is not allowing. But if you want to design,
you have to give expansion joint.
Yeah, what we are doing is we are dividing the entire into 3 parts. Yes, right.
Okay, so something similar to this.
Yes.
Now see, when you are determining your mass of this complete structure, you add mass of this structure, mass of this structure, mass of this structure. Okay.
Right.
So you get some mass center. Let's say this is my mass center. Okay. Then you determine your stiffness also. Somewhere here, I don't know exactly where it will be. So generally you will get torsion, right?
Right, yes.
So this is the things happening here. Now in this case, whatever procedure we have explained here, so you can try to satisfy, because if you make rigid this structure and this structure, so it will have torsional resistance. Okay, so you have to provide the vertical resisting member appropriately in this and this structure, but not effective much in this structure, what I understand. Okay. So you can try, have some iterations. What? Yes.
The thing is, again, that block has.
Yes.
Yeah, again, that block is having a 6. I mean, not having like a office block, right? See, office block. If that rectangle is an office. Yeah.
In between
the rect.
So in between the
condition. I understood. The condition is as much as possible you try to locate at the periphery. But if there is no option, so you have to increase the size of your members. That thing you can do. And ultimately, even after doing lot of trials and iterations, if you are not reaching the satisfiable condition, then you have to either go for dynamic analysis, or if the condition according to code, displacement max and displacement mean is more than 2, or according to new code, whatever is limit given, if it is more than that, then you have to reject that configuration if you are following the code.
Mr. Mohan, my one
Sir.
question is that
Yes.
the block 1, 2, 3, I can see 3 blocks. Okay.
Yes.
Block 1 will have a separate behavior if it is separated from the other two. Okay.
Right.
If let's assume block 1 does not have torsion in it. If
Hmm.
block 2 does not have torsion in it, which is the same as block 1 size. Okay. So, and third block is your longer direction. Okay. So
Right.
you are actually designing independently the 3 blocks, or you are combining the behavior of 3 blocks, because as such it is separated. So you cannot
Uh,
combine the behavior.
Yeah, actually,
So
I
why,
am
why
doing.
you are considering the torsion for the entire setup? I am not able to get that part.
See, here the
No.
condition is corridor is common corridor is provided. The structure will be separated only when corridor is not provided. So either to satisfy the condition, you can avoid the corridor, then
No,
design the
corridor can be provided, but that
hmm.
corridor will be on the expansion joint. It will not.
Yes,
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 yes.
Yeah. So
that's
Uh,
during
that's what I initially suggested actually, to have the joints instead of connecting with rigid members.
because if you combine the three, then you have to go for the time history analysis. There is no other option to do it, and
Hmm.
that is the only way
Okay.
out of it. Because
Okay.
it is not approved by the code, so you have to prove it. It is okay, and that is only by the time history analysis you can do that.
Okay, sir. So.
So if you want to have a corridor in between the two buildings, okay, you can have a let's say uh, uh, what we say that expansion gap is there, or some uh, bearings are also there. Okay, you can keep it on that if required. Not on all floors. If it is on all floors, then it is quite difficult. If it is on specific floor, then you can put it on bearing. If it is on all floor, then the only way is expansion joint, or you do dynamic time history analysis.
Time history. Okay. So if it is went for IIT approval,
Yeah.
so what they might ask, I think they will ask time history analysis.
In
The first
IIT, if
question
you
is
come for approval, then
Yes.
what we do is, because we also do the proof checking.
Hmm.
So
Right.
it depends on what actually you want to get from us. So the client, what they ask is to verify the model, what it is satisfying or not. So we'll ask you a structural model.
Hmm.
Then if you have done dynamic analysis, the ground motions, what you have used, and the basis on what you have selected those ground motions. Okay.
Okay.
So these
Okay.
things will be asked, and relevant drawings, documents, whatever you have regarding your structure.
Fine. Fine. Okay. Thank you. Thank you. And one more, that in your office, in your example one, so can you show that? So in the corners you have added the shear walls, right?
Mm-hmm.
So those are, I think those are columns or shear walls?
Shear walls,
Share was,
but I have modeled using
Shear.
the frame element.
Oh, okay, okay then. So in practical, if we model as a column, it frame element, I mean, it is coming outside from the block. So whereas in practical, it is inside the block, right?
No, this is actually just an example. So already grid was placed here, so I have plotted here.
Yes.
It's not like in actual structure you'll have like that.
Right.
It's
Is
just
there,
an example.
see,
so
is
in
there any change?
actual what you can do, L shape you can provide at the corner.
Yeah.
That is one way to do it.
You can
No,
provide L shape, either you just bring it inside. So your external edge will be located at the corner. You can do that
so
also.
is there any change if we model like this? If we not move, see in drawing, we'll move it.
No, there will be problem. If you are
There will be a
drawing
problem.
means modeling like that, but constructing in different way, there will be problem.
There will
So
be a problem.
always it is recommended, whatever you're doing at site, same thing you implement in the computer model.
Okay. Okay. Done.
Sir,
Thank you.
we will be modeling center to center diagrams, no sir, but beams we will be having some eccentricities.
Yes.
Instead, we are using offset option, but I don't know
Offset you
in
have to
ETABS.
use. If there is offset, in ETAB also it is there. You have to, if your beam is located with some offset, you have to model it as an offset only, not center to center.
So how much change it will affect on these parts? I mean irregularities. If we don't use offset.
Irregularity. It depends on how much offset. Again, it is similar to eccentricity. As you are increasing eccentricity, your result will be different.
Okay. If it is, I mean, the offset is will be around 300, 400 like that. So can we
it is
ignore?
significant. No, it is significant.
No. Okay. See, in general,
if it is
we
like,
have a rectangular columns, right? So if it is a column of around 600 by 1 meter, so if it is, if the beam is not connected to the center, so how much will affect on the structure?
It will affect, that's what I told, depending on sizes, how much offset you are giving. As you said, it is having 1 meter dimension in one direction. So you are connecting at the center in your model, but connecting at the edge in your actual construction. So there will be offset of around 400 to 500 mm.
Yes,
okay.
Right.
So that is significant. So why to go for center to center? In software option is available, you go for offset modeling instead of going for center to center.
Yeah, but offset modeling is taking too much time. So in general,
So I would see all these things are like for let's say high-rise buildings. I understand that remodeling takes a lot of time, and we don't have that much time to model in practical projects. So in that scenario, you can just recheck later on, but it should not give significant difference. That is the only thing. So you should keep a benchmark that remodeling is when required, because it takes around 15 days to give the output when you remodel it and take the results. So that condition is faced. So because there is some changes down the line, so all those changes cannot be modeled. Uh, Depending on the that timeline, it is all dependent on that. So considering that, if it is jeopardizing the situation, then you should remodel. Otherwise, you can have your free trials. Okay, that is the time when you can think that when to remodel, when not to remodel. So your groundwork will help you in that situation, rather than because there is no thumb rule. No, all will say that you should model correctly. All offset should be there. Orientation in the plan as well as your model should be correct. All those things will come is expected. Okay, so how much practically you can avoid and how much technically is required, you have to first do your groundwork on that. I would suggest you to have some few trials on your own building. That will help you decide better when to
Actually, this
remodel,
is
when
the
not to remodel.
basis. So as it depends on the eccentricity, so there will be some limiting value acceptable up to this eccentricity. If you have offset, you can ignore. If eccentricity is more than that, you should not ignore. So it will come to know only when you do some trial with some model.
There is model to model, simple model, complex model. What is the arrangement that you have? So all those things are critical in this.
Yes, sir. Okay. Thank you, sir. Thank you.
Yeah, one more thing. You told due to eccentricity, torsionality, there will be huge torsion on the beams. Correct? Because of the center of mass and center of rigidity, it will create some torsion on the beams and also columns and walls.
No, see, when we talk about the torsional eccentricity of the structure, means torsional irregularity of the structure, we are not telling the torsion is coming only in the beam. The torsion is coming in the whole structure. Your floor diaphragm is rotating.
Correct.
So your beam will be affected, your columns will be affected, everything will be affected.
Correct. What my question is, your beams you will take your torsion, will design it. Okay, na? When come to torsion irregularity, there will be, it will induce some torsion forces. While designing the beams, the software also it will take it automatically. It will design beam. But coming to column and walls, the torsion forces will be there. So how to tackle that one? Because the software will not take these torsion forces. It will take only moments and share. Okay.
No, torsion will
This
be taken by software automatically. Why you are worried about
For
this?
wall design and column, it will not take. For
Now,
beam,
how,
it is having option. Beam, you are having option. For beam, you are having as for IS456 procedure, it will design. Okay. But coming to columns and walls, it will not take this additional torsion forces while designing the reinforcement.
Okay.
This will be ignored simply. It will be ignored simply because you are designing it for moments and shear, not for the torsion forces in the walls and columns. That what you are calling is a wrapping torsion. Okay. That wrapping torsion you have to consider as per the ACFI code procedure, but Indian code is silent on that one.
Okay. Actually, I have to look at this.
Because the software will not take this. Software will not take this torsion forces while designing the shear reinforcement for columns and walls.
And that point is okay. When you are going to the design of shear reinforcement, maybe that procedure is not available. But what I mean to say is, when torsion is introduced in your model, the demand force due to that torsion will be coming to the column automatically. So your member will be designed for that forces. That is there.
No. Column it will come, but that torsion you are not considering in the design of the column. That is I'm telling. Your reinforcement will be designed based on the moment and shear, not on the torsion forces. In the model, in the software, it will be there. Torsion will be there. In the wall, also torsion will be there.
What you are trying to say is that we are designing for the principal directions, okay, X and Y, okay, not the column is twisting in the column is not considered as design. That is what you are
Because
suggesting,
software
right?
will not take that.
So, what provision we have that whatever the additional moments are coming, okay, so that is converted into shear and moment. Sorry, that shear will take form of additional moment to be taken by the column. So that needs to be checked because design for twist in the column, I don't think it is directly considered, but only way is taken as equivalent shear that we
No.
get, an
It will not
equivalent
convert.
moment.
It will not convert because beam. If you observe beam, software will take moment and torsion. When you give design command in the beam design,
Simple
then
directions
it will
only it
convert.
will take.
Then it will convert equivalent bending moment and equivalent shear. It will convert while designing it. But in the analysis, it will not convert.
No, design also we have design for torsion in IS code.
But
Okay,
that option is
for
not
member
there.
torsion.
If you right click on the ETA model, that option is not there. You just see what are the forces are considered in the shear wall design. It is actually analysis moments, moment and shear, not the torsion forces.
Sir, here one thing I would like to say. When you are saying analysis moments, that the moments because of that torsion is also coming to the column. Okay.
Yes.
But when you are saying the design and detailing, so design part maybe the procedure what follows, that maybe they will not consider the torsion directly. That I am not aware. That I am not aware about. I have to check that. But in analysis, the effect of torsion will be considered in your model automatically. That you don't have to worry about.
It will come. But while designing it, you are ignoring it. Analysis, it will come.
In analysis, if you are suppose you have the moment of 100 kilonewton meter ignoring the torsion, and the moment of 150 kilonewton meter when you are considering the torsion. So obviously you are designing for higher moments, right?
Moment you are designing it, but torsion force you are again you're ignoring, that your equivalent bending moment and shear you are not checking for the wall design, like beam
For
design.
which reinforcement are you talking about? The shear reinforcement?
Yeah, shear while designing the beam, how we are converting based on the analysis forces, and torsion forces, you are converting the torsion into equivalent bending moment and shear, correct?
Yes.
Accordingly, your stirrups will be given. Stirrups and reinforcement will be given. But coming to the wall,
one minute. Now I got your question. 1 minute. Give me just 2 minutes.
So that's why code is imposed 65% what you were told earlier. You should avoid totally torsion.
See, so give me 2 minutes, okay? Give me 2 minutes. This is your moment, right?
Yes.
This is your moment.
Yeah.
Now, this moment can be because of uniaxial forces or can be because of torsional forces. Okay. So what software does is whatever force is coming to the structure, it will convert these forces into unidirectional force components for each vertical members. So the rotational moment, what is acting in the floor mass level, means floor level, that will be distributed to each vertical resisting member in terms of movements in x direction and movements in y directions. Okay. So although your structure is having torsion, but you are not designing your columns for torsion. You are designing columns for uniaxial movements only, but that
Yes,
uniaxial movement is coming from the torsion.
correct.
So you are indirectly taking effect of torsion. So this is what I want to say. Torsion is considered. It is not like torsion is ignored when you are designing your member.
Okay, but if I consider movement is okay, but if I take output forces from the wall, it will give moments, shear, and torsion. Okay, analysis moment. If you are telling that whatever the torsion is due to torsion, that moments are created in the walls. You are telling shear also is created in the wall. But why should
Yes.
the in the analysis torsion should not come? You know, that whatever the torsion 100 kN, it is already converted in the analysis moment. Additional like that you are telling additional moment and additional share you are telling, correct?
Yes. Yes. So this you
Because
can compare. You model two towers separately. In one you ignore the torsion, another one you consider the torsion and check what is the member forces coming. Then you'll get to know whether it is considered or not.
torsion, how can you ignore in the walls? Modifier you are telling.
No, you lock the torsional degrees of freedom in your model. So that way your torsion will not be there in your structure. Then check what is the member forces coming. Then unlock the torsional degrees of freedom and check what is the member forces coming. You'll get to know the difference.
So that is on it is there, but I need to understand whether it considers or not. Then because beam you are doing the same principle. Beam also you're doing the same principle. If you're designing the beam the same principle, then the same principle will apply to walls and columns. I'm telling in that way. But why we are now in the beam while designing the beam, it again calculates the torsion forces for the additional while designing
Prasanna,
the output.
I would add this. Our beam and columns are 2D elements, and shear wall is, though it is a, let's say, taken as a, what's a PF, okay, but mostly it is working as a 2D element, not as a 3D element, right? That's why third direction force is not considered for design. So if you give specific instruction that third direction force is for design, then only it can take effect. Otherwise, it will convert the third direction into the two principal directions, the additional shear, and that,
That need to be ensured. That need to
yeah,
be ensured because
yeah,
that
yeah,
is the confusion.
yeah.
Because beam
So,
you're doing it same principle. Why column and beam? Then beam should also you should ignore. No, my question is beam should also ignore the torsion while designing. If already moment is coming in the analysis by considering that due to the torsion forces, then you should ignore it. No, while designing the beams. In any type, if you design beams, the torsion forces will
so
it will
see
take
what
the right
happens
right.
that column has a shear modulus G, based on which the stiffness in the twisting direction gets introduced in the software, and that converts the twist into the shears. So this effect you can see in the shear force mostly, and that shear
Yeah,
force
yeah.
will lead to the additional moment.
Yeah,
So
that is correct or not, we
uh,
don't know. That is correct or not, we don't know.
so what you can do, take one column, okay, take a portal frame, take one column, apply a lateral force, okay, and in the same thing, what you do is you apply eccentric force, okay. So in that you can check what moment change is happening in that same particular column. So one single column or a portal frame, you can evaluate with respect to that and check the design. That will give the final output basically. So you restrain at
Okay.
the top of the column, remove the restraint and apply in the diagonal direction. So you can apply the lateral force 0 degree, 90 degree, and also in 45 degree. So what change
Okay.
is coming in the shear forces, that you can check, and whether that design is satisfying for that column or not. So manual versus software, you can check that model.
Okay.
Okay, so that stiffness, your torsional stiffness, once you calculate, you can check manually.
Okay,
So
we'll
column
verify
is
it because that is
yeah,
that one
yeah.
because nobody don't know whether it is the torsion should be taken or not in the walls. That's why I'm checking. We'll
So
also
that is
verify it.
converted into shear, basically. Torsion, all
Okay.
torsions are converted to shear in 2D elements.
Mm-hmm. Okay.
So that way only it works mostly.
Yeah. That justification need to be checked. Okay.
Yeah. So we have a time constraint. So let us have a photograph first. So I would
Mm.
request Tajul to unshare the screen, and we can on the camera and have a photograph together for this particular
Okay.
session.
Okay.
So all can on the camera. So not all have opened their cameras. I would request all to open the means on their cameras. So just hold on, otherwise I will have to. All have not on their camera till now. Sayyed is there, Pradeep is there, Anil Kumar, all can on their cameras. Just a second. Let me check all have on or not. Okay, please smile. I'll just take a screenshot for the today's session. Okay, so all can off the camera if required. So
Okay,
I
thank
have
you
few
everyone
few
for
few few
participation.
review. I have some few points to finally conclude on to the today's session. So I thank Tajul for taking the session from the scratch, the basics. That is from the first mode to the modal analysis, manual calculation in MATLAB, ETABS, that I think many people would have done. I myself have also done. Uh, and the difference, what I can say is the X and Y direction. Let's say for two buildings are there, for the one podium connected, two buildings nearby are there. If they are anyway connected to each other or not connected to each other. But if it is a high-rise building and the difference in the time period of the two towers is has a difference of 0.2 second, let's say 0.8, 0.82 second, or let's say 3 second and 3.2 second, then the displacement difference is around 20 mm for that is on the higher side. So 10 to 20 mm, the difference in the displacement comes out to be. So manual versus software, if you are designing a building or doing something different from the software, then you should be very careful. Whatever you are doing, it should match with the procedure. And mostly when we see do the finite element analysis, then the distributed mass system is used. So your diagonal mass that you do for the rigid slab does not hold good. So from 3 degree of freedom, we go to 6 degree of freedom. In steel structures, when we go for the torsion of each element, then it goes to 9 degree of freedom. Okay, so ETAPS does not have 9 degree of freedom, but SAP 2000 has 9 degree of freedom. So if you are doing it SAP 2000, then again you have to go to that limit of evaluating it manually. And one part is related to chord rotation. So what Tajul had explained, the theta. Okay, so theta is the measure, and the code also they have written for the chord rotation. So chord is the edge of the slabs. Okay, the building edge of the building. So whatever direction you are considering X or Y, corresponding chords, how much it is getting rotated, that has to be checked. That can be checked in the software by two ends if it is a rectangle. If it is a plus shaped building, then you have to take the worst case, because whatever is twisting more, okay, that you have to check, and you have to consider the worst scenario of that, because it is not a square type or rectangle type building. So for different shapes, you have to select for the worst deformation criteria for the torsional check. And up to 1.2 it is okay. 1.2 to 1.5 the deformation is happening, theta is more, okay. Then you have to do the stiffness change, okay, so that it is limited to 1.2 as per IS code. If you go as per ASCE07, then they allow for 1.4 also, that is extreme torsional irregularity they allow in that particular case. So ETAPS is following ASCE software. So whenever you are checking, just check correctly, because it will not show the error as per the Indian code. It will show error if it is not as per the American code. So whatever the extreme torsional irregularity check you have to do it by yourself manually, not depend on the software. The software is not tuned to the IS code. It is tuned to the American code ASCE07 for calculating the factor 1.2, 1.4, 1.3. It will show in that values. So the theta is a radian, degree radian, that you can calculate manually only, not through software. Second is theta as a value from the software you will get, whether it is 1.2, 1.4, 1.5, or whatever it is. And going beyond 1.5, and when you are trying to prove it through software, what ASCE 41 is for the existing buildings. So when if you are evaluating an existing old building to the current code of practice, okay, then you will use the non-linear analysis, okay, not the linear analysis, because in that you have to use the best of the building capability. When you are designing the new building, you will use our IS code with linear analysis, because that is the only way to do for the new buildings. So old versus new, what method to use, how to do it, and what parameters are there, that I will explain. M theta divided by stiffness into distance square is very critical. However, in practical cases, we are not able to decide that. Okay, so once the authorities approve the plan, we don't have the option to change that plan. Okay, but as a structural engineer, how much you can add to that plan, okay, is very important, and that is the reason that architects also should be educated in this particular segment. I don't know whether at IIT, Roorkee architects also undergo through this course, but nowhere in the country they undergo a good session on torsional irregularities. The architects follow the aspect ratio, they follow the space planning, they follow the feel, and they follow the arrangement. But strategic location of the structural elements is not planned by them. And finally, you also don't get to choose it. Uh, but that is the reason the code has come up with a criteria. So previously, structural engineers did not have any basis to do it, and many people had told that architects are not allowing. So now the change has brought through by the code. The code is the criteria that is telling you now, giving the basis to the architect and to the builder that you cannot make it like this. Okay. And this presentation today gives you more confidence and more clarity that code clause have not come out of thin air. Okay, they have come out of some basis which must be followed. So it has to be followed, and to the maximum extent, because you will not be able to justify the ductility part later on. So you are doing linear analysis, you don't know exact ductility under torsional condition. If the building is failing, okay, then you will be under serious condition. But as the code has now come into picture, uh, I don't think any approving authority like IIT, like we had taken approval from IIT Bombay, so we have followed all the code clauses and given each parameter separately for approval. So that way the practice has to improve, and input from structural engineer has to reach to the builder and the architect team that this is possible and this is not possible. And that way the code is instrumental, and we should not challenge the code saying that the clauses are not right. Torsion in first mode, second mode, third mode, wherever it is not going to change the ultimate response is not correct. So the first video that we saw today also explained on the ductility part. Second is the shear participation. So columns or vertical elements are weak in shear. Okay, so their biggest enemy is shear. So by torsion, the shear gets into more into picture. In routine translational case, the shear will increase by 20% at least. So in all those scenarios, it is wise to practice what is mentioned in the code. And if you want to challenge it, you should have a better design to prove for it. So this should give you more confidence, more clarity, and how to manage torsion. So the challenge in this session was that to clarify what should we do in case of torsion and why these clauses have come into picture. So I think we have tried to answer it today. And if you have any more queries or you have some challenging situations that you are facing, you can contact us separately on this. So thank you, Prasanna. Thank you, Tajul. You have any last words to say?
Yeah, thank you. Thank you everyone for participating, and hope we will meet again with some other interesting topics. And thank you, Bhushan sir, for invitation for this presentation.
Yeah, thank you. Thank you for the nice
Yeah.
presentation. Thank you all for joining and taking the interest.
Okay, bye bye.
Yeah, bye.
Thank you. Thank you. Bye.